Let's look at interference in thin films. These are thin films where the thickness of the film is comparable to the wavelength of light. Oftentimes what we'll see is we'll be dealing with thicknesses that are approaching 1/2 or even 1/4 of the wavelength of light. So in looking at these, it's important to understand that as the light reflects off of these films, there is going to be the possibility of a phase change. But there's also going to be the possibility of phase change as the light goes from the front surface to the back surface and reflects off of that. So let's just take a look at the rules first of all. Without explaining why, we're going to look at going from a lower index to a higher index and understand that as we go from the lower index to a higher index material and reflect off of that, we are going to get 180 degrees phase shift in this reflected light. Now, this is analogous to a wave on a string. If I tie one end of the string to something that is fixed and I send a pulse toward that fixed end, as it reflects off the fixed end, that pulse is going to invert or experience a phase change of 180 degrees. So if I have a peak coming in here, that will reflect as a valley coming off there. There will be 180 degrees phase shift going from a lower index material to a higher index material. Again, without explaining why, if we go from a higher index of material to a lower index, that let's say from glass to air, this type of reflection is going to result in no phase shift. This is analogous to a rope being connected to a movable link, which can go up and down this pole as the wave comes in. And again, without explaining why, we don't get a phase shift in this particular case when we have a free support on the other end. So again, going from high to low, no phase shift occurs. Let's take a look at one of the simplest examples of the interference on a thin film. This is a soap bubble. And of course, the soap bubble forms because we have a surfactant there, some type of detergent, some type of soap. And that's going to create a two-surface fluid with the water sandwiched in between without going too much into the chemistry. Detergents have a hydrophilic and a hydrophobic end. And the inside of the film is going to be water, which is in contact with the hydrophilic end of the detergent. So in any case, long story short, we get a very thin film. It is comparable to the wavelength of light. Now, at the very top, it's extremely thin. The thinnest part of this soap bubble doesn't produce any type of interference colors, okay? It just appears like we'd expect a thin film to appear. But we notice as it starts getting thicker, and again, gravity is making it thicker at the bottom and thinner at the top, as it gets thicker, we notice this blue line right here. The reason why this happens is the light reflecting off the front surface and the light reflecting off the back surface are experiencing interference. For the blue light, this is thin enough where the blue light is going to experience constructive interference. All right. All the other colors are experiencing destructive interference. As it gets thicker, however, we notice that the colors shift to longer wavelengths, all the way up to this red. Now we get destructive interference for the blue light and constructive interference for the red light. We've gotten thick enough where we're now the right condition to reflect red light and not the correct condition to reflect blue light. We get thicker again, and now we see that blue light is again experiencing constructive interference and other colors are experiencing destructive, to green, to yellow, and then we get this magenta color where we actually get multiple colors which are experiencing constructive interference. In this particular case, both red and blue are experiencing constructive interference. Okay, now that we know exactly when these interference colors appear, let's see why they appear the way that they do. We have a few things that we've got to keep in mind, facts to remember, that when we reflect off of a higher index material, such as the water in the soap bubble, we're going to experience a 180-degree phase shift. If we reflect off the backside of the soap bubble, the water is higher index than the air, we're going to get no phase shift. So we've got to keep that in mind when we do this analysis. The next thing we have to take into account is that going to a higher index material will result in a smaller wavelength. So what we have is, when we're looking at interference conditions, we are not looking at the wavelength of light in air. For instance, green light is around 500 nanometers. If we were to go to another medium, such as a medium with an index of 2, it would have half the wavelength. So again, we have to consider not just what the wavelength of light is in air, we have to consider what the wavelength of light is in the medium from which the film is made from. The wavelength of light in any medium is equal to the wavelength in air, or vacuum really, divided by the index of refraction. So let's take a look at the case where we're reflecting off of this soap bubble. And this is going to be the same case as it would be for any very thin film. We have air on both sides. We have water in between. And on the front side, this ray is going to reflect off the front surface. And because we're going from lower to higher index material, we are experiencing 180 degrees phase change. Now, for the second surface, after the ray penetrates the water, some is reflected, some goes down. This second reflection off the back surface experiences no phase change here. If this thickness were perhaps 1/4 the wavelength of light, okay, 1/4 of the wavelength of light inside here, it would experience a quarter of a wavelength change and a quarter of a wavelength change. If it's 1/2, 1/2 plus 1/2 is a whole wavelength, or 360 degrees phase change, which is exactly the same as 0 degrees. So again, if this soap bubble had 1/2 the wavelength thickness of a particular color of light, we would get 180 degrees phase change and a 0 degrees phase change. These two rays would destructively interfere, and therefore that color would not be reflected. So when we looked at that first blue fringe, this was probably the condition for the red light, that the thickness of this was comparable to half the wavelength of the red light, and we're getting destructive interference. For the condition of constructive interference, we would need a slightly different situation. Okay, so destructive interference, we can do this. Once again, we're going to say it's going to make 2 trips. It's going to go down, then it's going to go up for the second ray, which is being reflected. So when we talk about this, we can say that for twice the index of refraction times the thickness, okay, if that's equal to m being an integer, times the wavelength of light, we are going to get destructive interference. Or basically, if the thickness is equal to some integer times the wavelength divided by the index, remember the wavelength divided by the index is the actual wavelength of light inside the water, okay? Again, destructive interference. So let's take for m equals 1, the wavelength divided by 2 means that if this is half a wavelength thick, we are going to get destructive interference. That's half a wavelength for the light traveling through this water. For constructive interference, our conditions are a little bit different. Now consider, once again, this light is going to bounce off here and get a 180 degree phase change. Now, what if this is only 1/4 of a wavelength? Then it gets 1/4 of a phase change, I should say wave length change, another quarter wavelength change, which is 180 degrees. Both of these are in phase, so we're going to get a strong reflection at that particular wavelength. That condition, once again, is 2nt is equal to m plus 1/2, okay? Again, if we increase this whole distance by another half, you're just adding another 360-degree phase change. You're going to get the same result. But here we see the thickness is equal to m plus 1/2. So if m equals 0, it's 1/2. We got another 2 in the denominator down here. If this bubble thickness is 1/4 of the wavelength of light in water, that is going to be strongly reflected. Okay, constructive interference. So again, looking back at our bubble right here, this first, blue fringe, it probably corresponded to about 1/4 of a wavelength of the blue light, and blue light being around 460 nanometers. That was 1/2 the wavelength of red light. I know it's not quite 900 nanometers, but it's sort of approaching that. And therefore, constructive interference for blue light, destructive interference for red light. And again, that's for the simplest case where we just have a single film. Here we just have a soap bubble. There's nothing behind it. So the front side has air, the back side has air, and in between it, we have our soap bubble. And again, you can see these interference colors on the soap bubble right here. This situation is a little more complex, where you can see some magenta, you can see some blue, you can see some yellow. So really what we're seeing is a great deal of variation in the thickness throughout the bubble. But also it has to do with the angle that it's coming into. Here is a different situation. Now what we've done is we put an oil on top of water. So in this case, we are going from a low index, we're going from air, to a higher index, oil, to an even higher index, water. What do we do for this type of situation? Well, for this type of situation, we have to consider the fact that both the first reflection and the second reflection are going to undergo a 180 degrees phase change. So we have to think this through. What exactly is going to happen to produce constructive interference? Well, the first reflection reflects off at 180 degrees. The second reflection, to get back to 180 degrees, we have to go 180 degrees, which is half a wavelength, plus another 180 degrees, which is another half wavelength. Okay, so that our thickness is our thickness is 1/2 the wavelength to produce constructive interference. Okay, now this particular situation, where we have instead a 1/4 wavelength thickness, we are going to get the two reflected rays 180 degrees out of phase. Okay, this is a very, very important case, and we're going to call this the anti-reflection coating. You'll see why in a second. Now, the first ray comes in, it's reflected at 180 degrees. The second ray comes in, it receives 180 degrees phase change, but it also gets 90 degrees by traveling a 1/4 wavelength, another 90 degrees by traveling a 1/4 of a wavelength. Okay, so in this particular case, when it comes out, it is going to be at 360 degrees, effectively 0 compared to the 180 degrees. The two will be out of phase. And what's going to happen here is this reflection and this reflection are going to destructively interfere. Why is this important? Why do we care that we can reduce the reflection of these two beams? Well, the problem is when we have lenses or we have any optical device, these internal reflections off the glass surfaces are going to create something called lens flare. It's going to degrade the image. Sometimes lens flare is desirable from an artistic standpoint, but the contrast of the image is going to suffer due to these unwanted reflections that occur off of different lenses. So what we can do to normal glass, let's say that this is crown glass at about 1.52 for an index of refraction. We can coat it with a slightly lower index of refraction material, and the first and the second reflections we're going to cancel each other out, and effectively we won't have a lot of these internal reflections. Now, the condition for this, since we've gone 180-degree phase change, another 180 degrees phase change, is that effectively the thickness of this coating is going to be equal to the wavelength of light and air divided by N2, which is the index of refraction of the coating, divided by 4. So 1/4 of a wavelength thickness for whatever material that we're using. So again, you have to remember, if you're dealing with 500 nanometer light, the wavelength inside here is actually 500 nanometers divided by 1.4, okay? So we've got to take that into account when we're doing these calculations. Okay, so this quarter wavelength coating is, again, used for lenses, and we can oftentimes see this coating, which results in a bluish type reflection, because really the coatings that we use aren't matched for all wavelengths. They're 1/4 of a wavelength really for the middle of the visible spectrum. So we're sort of matching it for around 500 nanometers. So shorter wavelengths like blue light and very long wavelengths like red light will produce a sort of purplish type of reflection, bluish purplish type of reflection. Now, ideally, we want a material which is about 1.2 for an index of refraction if we're using crown glass. That will make the reflection of 1 and 2 equal. However, the best that we can do is really a material known as magnesium fluoride, which is a fairly tough material that we can coat these with, which has an index of 1.38. It's a little bit on the high side, which means the first reflection is going to be a little bit stronger than the second reflection. So instead of it completely reducing the reflection off of the lens, it's going to reduce the reflectivity from about 4% to 1%. Okay, so it's improving our situation by a factor of 4. Coating these lenses with magnesium fluoride is a lot better than not coating them at all. For flint glass, if we're using a higher index material, magnesium fluoride actually does quite well. We get a better performance, a much smaller reflection. But remember, with these camera lenses, when we're correcting for aberration, when we're trying to correct for field curvature, when we're trying to increase the field of view, we have very short focal lengths that we're dealing with. There's not just one lens that we need to coat in here. We need to coat every single lens inside there such that we don't get a lot of these stray reflections. Okay? And here is an example where eyeglasses are using don't have a reflective coating. You can see the reflection right here. And here's the same alignment, but here the woman is wearing glasses with this anti-reflection coating. And you're like, well, okay, so we have a little bit of reflection here. That really doesn't bother me. Well, not during the daytime, but if you drive at night, you can see what the anti-reflective coating does. We don't get what we call this lens flare. And here's with the lens flare, it makes it more difficult to make out the image. We get too much stray light reflecting from the front surface and the back surface of the glass, making it harder to see what we're looking at in these situations where you're having to face these bright headlights. So anti-reflective coatings, if you have glasses and they tell you that, oh, we'll put anti-reflective coatings on it for an extra cost, know what you're paying for. If you have trouble seeing at night wearing glasses with this lens flare, then you probably want to switch to an anti-reflective coating and pay that extra money. I don't have anti-reflective coatings on my glasses. Maybe I'm cheap, but the lens flare never really bothered me very much. We'll see how that goes as my vision continues to change. But again, camera lenses, sometimes lens flare is used for effect. This illustration here shows really, really bad lens flare, probably due to somebody taking a picture with a flash in the background. And you can see every single surface on every single lens inside here can produce a reflection, which actually results in multiple reflections off of front sides and back sides of the lenses. So AR coatings, again, very, very important for high quality optics where you want to eliminate some of these problems. And you'll see these, in any quality optical instrument. Here is a telescope. This front corrector lens, clearly has a coating on it, probably the magnesium fluoride. You can see these lenses right here. They have sort of that purplish reflective color to them. Again, all of these also have that anti-reflective coating, because when you're looking at things at night, lens flare can really degrade the image and really hurt contrast of what you're trying to look at, especially if you're looking at very, very dim objects. This is also used in photovoltaics. The problem with silicon is it has an extremely high index of refraction, okay? The reason why we have reflection in the first place is the light is going from 1 index of refraction, around 1, to a higher index of refraction, if off glass, 1.5. The amount of reflection is very much connected with the change in the index of refraction. So for instance, if it's just off of crown glass, as we said, the reflection is about 4%, okay? If it's off silicon, which has a very high index of refraction in the visible part of the spectrum, that reflection can result in a significant amount of energy being lost. I'm not sure exactly what the amount of reflected light would be, but it could be over 10%, so you're losing all that energy. To improve the performance, what they actually do is they coat the silicon with silicon monoxide. And this has an index of refraction of 1.45 and creates an excellent match between the two interfaces. Now, by making this 1/4 of a wavelength thick, now I got this wrong here. It's not wavelength divided by N2. The thickness is actually the wavelength divided by 4 times N2. We get a strong anti-reflective surface, and thus we get most of the light down to the silicon, where it's going to be converted into electricity. Alternatively, instead of using 1/4 wavelength stacks, we can use what's called a 1/2 wavelength stack. And in this case, we are going to get strong constructive interference. That means that the reflections are going to come together all in phase and therefore produce a much stronger reflected light. Now, why would you want that? Well, the problem with metallic mirrors is they're about 90% reflective at best. In some cases, we want better performance. In that case, we can stack these alternate layers of high and low index material. This will create a very strong backward reflection. We call these dielectric mirrors because instead of using metal, which obviously being metallic is not a dielectric, dielectric materials like silicon dioxide are using a change in index of refraction and constructive interference to produce a reflection rather than the free electrons in the metal creating the reflection, okay? And you can get nearly perfect reflection. You can get 99.999% reflectivity as you add more and more layers. And this is especially useful when we're doing things like using lasers, okay? Lasers inside a laser cavity, the efficiency of a laser or the gain in a laser is, I should say the efficiency in the laser is very much related to the reflectivity of the mirrors in the resonant cavity. Again, in any of these cases, a 1/4 wavelength, which is used for anti-reflective coatings, or 1/2 wavelength, which is used for dielectric mirrors, the thickness of the film is going to be very much connected with the wavelengths that are reflected and the wavelengths that are not reflected. Okay? The larger the change in index of refraction, the larger the spread, or the larger the bandwidth of light that can be reflected. But again, as you can see with these oil droplets here, they are very selective in what colors that they reflect. And again, you can see different types of interference, or at least interference colors. And obviously, when the thickness of the soap bubble is very, very thin, you don't get any preferential reflection. In this case, all the wavelengths are reflected about equally, and then you get to some of your first interference. Well, here blue is strongly reflected. Here, green is mostly reflected, but you still have some blue and some red. Here, red and blue to produce that magenta color. And then again, as you go on, the thickness gets greater and greater. You get different interference conditions for different wavelengths. So, this probably illustrates best how these interference conditions lead to the different colors that you see. And again, the red wavelength is much larger than the blue wavelength. So constructive and destructive interference is going to happen for different thicknesses. And as a bubble gets thicker and thicker, the coherence of the light becomes less and less. So, really large thicknesses of these films are not going to produce interference colors. Again, there's our soap bubble again. Gravity making it thicker at the bottom, thinner at the top. All colors being reflected. Red being preferentially reflected, blue being preferentially reflected, and then other interference colors down here. Now, when we're doing the calculations for interference in thin films, again, if it's a single layer, like a soap bubble, typically going back to what we were looking at, I've got to go all the way back to the soap bubble. Typically, when we're looking at this, for a quarter wavelength, that is when we're going to get a strong reflection, quarter of a wavelength. For a coating on top of glass, as is the case for anti-reflection coatings, that destructive interference happens at a quarter wavelength, and the constructive interference is going to happen at 1/2 of a wavelength. Okay, so it's different for a single layer compared to a layer on top of a high-index material like glass. Here's another application of using interference to basically analyze, in this case, we're going to analyze a lens. When lenses were first ground, they were ground with not a whole lot of tools to analyze their shape. Basically, spherical shape was the easiest to grind, so that most lenses were ground spherically. But how do you actually determine whether or not what we are creating here is a perfect sphere? Well, something interesting happens when we take a spherical surface and we place it on what's known as an optical flat. We have a perfectly flat surface, okay? Another optical surface. We have this curved surface. You are going to have an air gap here, which is going to have different conditions of interference, as we see, shown by this equation right here, which relates the radius of curvature to the wavelength and to the distance from the center of the lens. Basically, you get this bullseye pattern right here if the lens is the correct shape. If it's not the correct shape, this bullseye pattern will be somewhat deformed. and the lens maker could go back and grind it to the proper shape. But the old way of correctly obtaining the proper shape to a spherical lens was to use these optical flats and see that this was a perfect bullseye. Now, obviously, this is somewhat distorted. So this lens that we see right here has some astigmatism to it. It's curved more along this axis than this axis. And again, this pattern of light and dark rings, they're known as Newton rings, and they're very, very important, or they were very, very important to the lens makers. They tried to perfect the shape of the different lenses and grind them to their proper radius of curvature. So basically, when we're looking at thin films and trying to figure out which colors are going to be reflected and which colors are not, we need to, first of all, understand what are the conditions of constructive and destructive interference, and also what is the wavelength inside the actual material. So again, if we have a single phase reversal, this is the case of the soap bubble, okay? You're going to get constructive interference when we have twice the index of refraction times the thickness is equal to some integer m plus 1/2 times lambda, okay? So constructive interference happens at a quarter of the wavelength, happens at 1 1/4 of the wavelength, 3/4 of a wavelength, so on and so forth, okay? Destructive interference, okay, that takes place at 1/2 of a wavelength thickness. Now, it's the opposite when we deal with going from a low index material to an even higher index material. There we're going to get two-phase reversals. So in this particular case, you're going to have destructive interference at a quarter of a wavelength. This is the case of the anti-reflective coating. And you're going to have constructive interference at half a wavelength. This is the half wave stack, also known as the dielectric mirror.